John Yundt, SunRay Scientific.
Here
Perfect.
we are.
John, stage is yours.
All right. Well, thank you very much. Thanks everybody for coming in today. Looking forward to presenting to you. We've been involved with TechBlick for some time now. So what I'm trying to show today is a little different version of some of what we presented in the past, maybe focused on some of the different types of applications we've been working on, some of the projects that we're currently involved in, and some of the alternative uses for our technology. So the agenda really quickly is to give a brief description for those who are not familiar with our anisotropic conductive adhesive epoxy, to talk a little bit about the technical attributes as well, then get into some potential advanced packaging applications and use cases. We'll talk about some of the potential markets. Actually, I kind of reversed that and put the markets up front, and then we'll try to save some time for a quick Q&A session. I realize we're a little behind schedule, so I'm going to try to get through this quickly for everyone. Starting off, just to level set what the technology is, this is a novel anisotropic epoxy technology. It is neither a film nor a traditional ECA. It's a deposited, printable, stencilable, or jettable material that's made up of ferromagnetic particles. These are similar to the previous presentation that you heard. We achieve alignment and we achieve a unique anisotropic conductive interconnect by way of similarly coated particles. Our particles are ferromagnetic, and then they can be coated with a range of precious metals, whether it's silver, gold, platinum. Traditionally silver. For some applications we use gold. These are deposited or dispersed very innovatively through a process that we've developed into a polymer epoxy matrix. Those are then deposited down onto the pads or areas where the interconnection is to be made via the range of application technologies available. We've used NJet from NScript. We've used stencil printing. We've used standard syringe dispense. So there's a range of ways this material can be deposited in its liquid form. And then you place the component down onto the surface of the ZTACH ACE material. The alignment of the particles achieved as soon as it comes out of pick and place, and after the components are placed down, by placing it down onto our ZMag pallet. So we get this vertical column alignment through the ZMag pallet. Those ferromagnetic particles within a matter of seconds begin to align and create columns. As it goes through the curing process, those columns are locked into place. And when it comes out of the reflow oven, you have perfectly aligned Z-axis interconnect between substrate, the conductive pads on the substrate and the pads on the component. We can cure at a range of 80 degrees C all the way up to 160 C. We also have in development a UV curable system. It's actually going into production on a very specific application for fine wire attach. And we are working on a shadow cured version of this technology that can cure fairly large components with shadow curing beneath, and that should be ready within the next year. This is not a system that requires any kind of pressure. So this is a pressureless system, only the pressure that's used to apply the component down onto the substrate. It also doesn't require patterning. So you place this under the entire area of the component, and obviously those Z-axis particles take care of eliminating any risk of shorting by creating very uniform columns. We eliminate the need for any solder bumping. We eliminate the need for any underfill as we create our own underfill, and in most cases, no encapsulation is required. So what you have as a result is a very strong structural electrical bond between the areas of interconnect. What also is achieved is good thermal dissipation. So anywhere where these columns that you see being formed, if they're not making an electrical interconnection between the conductive pads that have been printed down onto the substrate and the pads or bumps on the component, you get good thermal interface between those as well. And this is how it's done. A video on the left here will show that as soon as we're coming out of the pick and place machine and components are placed down onto the pallet, we get instant particle alignment. They continue these alignment process. And then what you're looking at here is a real-time, non-accelerated X-ray camera looking cross-sectionally through what I like to say is this forest of trees that are being formed. So we're creating all these columns. This technology here is our fine material, which can manage pitch down to 100 microns. We have an ultra-fine material that's proven effective down to 50 and 60 microns, and we're developing a material that can